Hello, everyone. Thank you very much for coming on my talk. Very glad to see you all. The topic of my talk is leveraging Spire for complex time allocation logic. It's maybe not close to everyone's heart, but I hope many of you will still get something out of this talk for your current problems you're working on at your daily job. So a little bit about me. I'm a software engineer at Evolution Gaming. I do Scala for over 4 years, along with Scala.js. I maintain 2 small projects on GitHub that are related to daytime things. And the last 2 years, I've been working on internal scheduling, big internal scheduling system, which the thing is that exposed me to all the problems I am discussing today. So Spire is a big library of mathematical abstractions. It contains a lot of tools. I'll be only discussing one today, which is intervals and interval sets. These people are core maintainers and creators of Spire. This slide is a credit to these wonderful people who made this library possible. So before we start digging into some code or examples, how many of you are familiar with the intervals, interval notation, and stuff like that? Please raise your hands. Okay, not that many that I expected. Good that I have some theory slides to fill the gaps. So let's take a look at real number intervals. These are kind of the most commonly known ones. Interval is a set of numbers which is defined by 2 boundaries. Each of the boundaries is either open or closed, meaning the open boundary doesn't include the boundary itself. The closed boundary includes the value at boundary itself. There are also special boundaries like negative infinity and positive infinity. This is the 4th interval from the top. The next one is the empty interval, which is also like the empty set. And there are also degraded intervals, which contain only 1 value. So real intervals basically all intervals have one important property, which is you can't iterate all the members. So even the smallest non-degraded interval has infinite number of elements, which is kind of interesting. So interval sets is a kind of natural extension of idea of interval. It's again a set of numbers, but contains from several disjoint intervals that are joined through the union operation. So there are some examples of interval sets. Let's take a look at some operations. So intervals and interval sets are sets of numbers. They kind of no different from regular sets. And that's why we can have all the operations that are related to sets. They will work on intervals as well. So these are examples of intersection and union. I hope many of you know how these work. This is kind of basic math. But some examples for those who maybe don't remember these vividly. So another operation that is interesting to us is a complement, or it's called inverse. This is basically all the elements that current interval or interval set does not contain. This is its complement. And it's defined with this, it's written with this tilde sign. And the last thing we'll look at is subtraction. I will not give examples here, but because it can be defined through existing operations, basically A minus B is A intersecting complement of B. So again, this is usual set algebra, which is applicable to intervals and interval sets because they are sets as well. Let's take a look at problems that are solved with intervals. Main kind of application of intervals is modeling uncertainty. We are functional programmers, and we know one data structure that models uncertainty, which is list, right? So instead of 1 value, you get several values, possibly several values. This is kind of one way of modeling uncertainty. Intervals are different in the sense that they model continuous uncertainty. So in case of list, you get some finite number of options for your result. Interval goes another path. It provides you with infinite amounts of kind of this uncertain results within some bounded range, or possibly unbounded range. So that's kind of the most kind of popular application of intervals. Also fuzzy calculations and complex multidimensional constraints, but the thing we are going to look at today is scheduling. And scheduling is possible to solve with intervals because intervals, by their nature, they don't require anything numeric from the underlying type. The only thing they require is actually order, the total order. We all know that total order from standard library ordering or CATS or Scala.js order. So that's the signature of Spire interval. And yeah, so we need to kind of try to make this work for time values, which will give us time intervals, right? So it turns out that we can provide order for time values, and there is one caveat here that there is actually at least 2 lawful orders for time values that have different, like kind of different semantics. So let's take a look at that. First one is strict, the strictest order possible, which uses compare to, and it considers 2 values equal only if the time zones are equal as well. So even if you have same instance, if they are located in different time zones, these are different. And the second one, which is also legit, but a little bit more relaxed, is the one that compares only instance. So we can have similar, like equal time values with different time zones. So depending on your application, on your requirements, both can make sense, so you have to just be aware of that. So given these instances, one of those, of course, we can now write this and use intervals for time. And this opens up quite a lot of possibilities. So let's not wait and dive into Spire API for intervals and interval sets. First thing on our agenda is bounds. This is very simple ADT, which has like this 4 types of bounds, which kind of closely models the things we were looking at the theoretical introduction. So these are negative infinity and positive infinity, open, close, value boundaries, and special kind of empty bound for modeling empty intervals. So there's nothing kind of complex here. Next thing is the interval itself. And this gets more interesting here because conceptual interval is just 2 bounds. You can see there's lower bound and upper bound. But what the difference here is that there's no public ADT tree available for you to kind of explore at runtime to pattern match over or stuff like that. So there are reasons for that. I'm not going to dive into that, but instead of ADT, we have some smart constructors. I just have to warn you, some of them might throw, so that this is not kind of purely functional, but there are probably performance applications. So this is more or less lower level thing, so probably throwing exceptions might make sense here. So these are rich enough for most of the applications. Like you can create any kind of interval with those. So to overview the interval API, there is lots of things. So you can check point membership. You can check intervals for subset or superset relation. You can calculate intersection. You can calculate complement and subtraction. These stand out because they, in general, can return 2 intervals. That's why they return a list. And also there is interval arithmetic, but we're not going to look into that. So complement and subtraction look kind of weird because they have this list. So to get the full power of expressiveness, we need interval sets. These were developed by Rudiger. This is very nice software. So thank you, Rudiger, for that. These are really amazing things. Let's quickly overview. So they go in 2 flavors, actually, interval trie and interval sequence. These are some properties. In the interest of time, I'm not going to dive deep here, but you can watch Rudiger's talk on last year's Scala World, which is called fast immutable interval sets. Here he goes into detail there on how they are structured under the hood, and this is one of the most amazing pieces of engineering I've ever seen, so definitely recommend this to watch. Interval set allows us to solve much more complex tasks. The API there is quite simple, so I'm not going to look into that. We'll just see some examples. So it's time to solve some tasks finally. First one is going to be some regular calendar scheduling that you mostly face every day when you open your Outlook or some other calendar application. So let's solve this simple task when we need to find possible slots for a meeting for these 3 people with additional requirements that the meeting has to last for 1 hour and must fit into the workday hours. So this one is actually pretty simple. We can solve it with bare hands, right? There's these 2 spots out there in the calendar that fit the requirements, but let's try to generalize it, use this example to build a more general solution. So actually now some code. We'll first define some helpers. So I try to put as little code as possible in one slide so that it's easy to understand. So there is entry is one interval, entries is interval set. In this case, it's interval sequence. And also we'll need a way to calculate duration of one interval, which is to be able to filter them by, so that we only get the slots that are at least 1 hour long. So in this case, this is a very kind of simplified version. We just we can calculate duration only for bounded interval where both boundaries contain some value. Any questions so far to this slide? No. Okay, we can proceed. So again, another slide with some preparational code which contains so we somehow must get the entries for these people. Here we'll just write them out as lists, but in the real world we'll get them from some database or some remote service. Workday is a special interval which is from 9 to 19, where daytime is just some helper that allows us to create a value on some day. So this is just, we take some day for our example, and this is 9 hours, now 9 a.m. on this day and 7 p.m. on the same day. And 1 hour duration is again for filtering. And now we are finally ready to solve the task, and the solution actually fits one slide. So first we merge all the entries together to get interval set of all periods when at least one person is working. So this is the period, the set of periods where we can't have a meeting because someone has some scheduled stuff to do. So what we do is we kind of start with empty. How do you use that? Empty. Okay, that was not a good idea. What's going on? Okay, it's back. This one, yeah. So we use empty sequence as a start, and then we using union operation, which is here, which is kind of this OR pipe in Spire. We add them up, and to get the result, the solution, we take a complement. So this will be all the periods where all 3 people are free to take a meeting, and we intersect it using AND operator with our workday. So this will get the list of possible solutions within the workday. And all that's left to do is to materialize the interval set into the list of intervals and filter to leave only the ones that at least 1 hour long. So that's our solution. It's quite expressive, quite readable, and a little bit mathematical, but we'll talk about it later. But still, it's rather nice, and if you run it, of course, you'll get the same slots that we found by hand in the beginning. So that's I have a Scasti worksheet. If you want to play around with that, it's all working. There's the same code that I show is on the web, on the cloud. Let's take a look at another task. It's kind of the same nature, but we'll have some different techniques there. Find all the periods where these 3 employees were working together at the same time. Again, the solution will fit on one slide easily. So here we'll again compile a set of periods where all people are working, but we'll not merge them into single one, but instead we'll build a interval sequence for each person. So here again, like for each of these guys, we build a set of their working entries. And then we'll just intersect them all together, starting with interval sequence is basically negative infinity to positive infinity. It's the set of all values. So we'll intersect them all over each other to get only the periods where all of them are working together. So that's a whole solution. We don't stop that. There's lots of other tasks that can be solved in the same expressive and really concise way. Yeah, so let's take a break, and who will tell me what kind of common, really popular functional programming concept kind of screaming out from these lines? Any guesses? Right, it sounds humanoid. So it's actually called Baud semi-lattice, if I pronounce this right. So, but for us, it may be the more convenient formulation would be idempotent commutative monoid. This is kind of nitty-gritty details. The most important thing to us are these set-based monoids. So these are not, again, specific to intervals or interval sets. These are like known instances for all kind of any kind of sets that have a common superset. So union monoid that uses empty set as an identity element, and intersection monoid which uses the set of all values as identity. So these are really kind of existence of these lawful instances provides us with a lot of functionality for free. We can use fold map and stuff like that for to work with intervals, which is really nice. And in the Scasti worksheet I provided, I actually use these instances instead of kind of this manual fold left operations. So our FP purists break is over. Let's proceed to some other problems we can solve with intervals, which is resource allocation. This is kind of example of probable kind of task that can be solved. Actually, the space of possible problems here is really, really wide. But in essence, you have some work to be done, which is defined as some like periods, basically shifts. For example, someone must stay at the cashier desk, right? So we need a person from one time to another. And we have some people that do actual work, so the schedule of the resources that we have, and we need to match these together, right? And we need to. There are really a lot of various constraints that need to be satisfied during this process. So the legislations, minimization of overtime work, minimization of idle kind of time when nobody, like when someone comes to work, right, and doesn't do anything. So it's kind of hard to provide some really simple example that shows some basic stuff, but instead I'll provide just a piece of possible solution that can be done in such tasks. So this is small kind of unit of solution of one of these problems. So we have a requirement, which is, again, remembering our aliases is an interval set. So basically we say that, for example, every day during 2018, somebody needs to work from 8 to 15, so for example. And the work is actual schedule when we have people that we know that, for example, John will come every odd day of the month, and Bob will come every even day of the month, for example, again, at the same time. And here we can quickly, using Spire, we can quickly calculate some metrics of this solution, which is the time that was covered. Actually, the resource matched the requirement. The time that was uncovered, so when we lack some people, the work needs to be done and there is no one. And use time when somebody is at work, but there is no work to be done, basically resource is wasted. Yeah, so that's kind of how I would start to approach these problems with using Spire intervals. So I would like to talk about another dimension of using Spire in real-world task, and this is a really important one, which is integration with your domain. So these days people pay more and more attention to relationship between business domain and the code, right? There's this rise of DDD techniques, ubiquitous language, and other things. And this is really great, so that's why I raised this topic. There is a huge argument against using Spire intervals directly in your applications, in your code, and the concern is that interval sets are too broad for most domains. So what I mean by that is, for example, for most domains, negative infinity doesn't mean anything. It doesn't, like, it's not representable by something in the domain itself. So, the problem here is that you can create values that do not mean anything in your domain. And when you do that, you basically creating problems for yourself, because you will have to throw exceptions eventually. And I'm sure most of you are not fans of throwing exception every now and then. So your programs must be able to only construct values that are valid in your domain. And this is why Spire intervals are kind of the low-level thing that you should kind of cover with your own domain logic, with your own domain structures. So there are lots of benefits of separating separating some domain-compliant data structures on top of Spire. So you still get all the power, but you kind of hide it inside the names that are more familiar to people who work with your domain. So it's control over serialization, control over various optimizations, and rich models, helper methods, and readability, and really lots of benefits. The only overhead is, of course, that you have now another set of data structures, but it's worth it, in my opinion. And there are some other concerns that I want to go over. The first one is, it's kind of the continuation of what I was talking on the previous slide, which is you have to really, before starting using that in your applications, you have to really think of what makes sense and what doesn't make sense. For example, does negative infinity make sense for you when you model your domain with Spire? Interval boundary constraints are also very important. So for example, if you don't take care, here you can get some degraded intervals, some edge cases when you intersect two intervals that have closed boundaries on the edges. You can get degraded interval. In some domains, this doesn't make sense. So you might need to use some consistent approach to using boundaries, right? So there's one example that we use in our domain, which is left boundary is closed, right boundary is open. This way, you won't get any degraded intervals ever. Precision constraints. This is very interesting, not only because this allows you to restrict the kind of values you can create, but also can allow you to use faster interval try for interval sets. There are details in Rudiger's talk, but basically even milliseconds precision. So if you don't need nanoseconds, you can use interval try, and this is nice. Ordering and equality semantics. So this one we talked about, but just you have to think about it when you kind of plug in your order instances into your code base. So this is another important thing. Try to avoid leaking the Spire abstraction in the domain level, so that you can eventually switch to something, or so that you don't get any exceptions from Spire, for example. So that's also important, so that the people who read the main code, they don't like see these mathematical operators like and, or, intersection, stuff like that. It should be readable in the domain terms. And there is a small caveat about this order constraint in the constructors for interval. So if you remember the type signature for interval, it's right in the constructor. So this poses some challenges for generic programming, for example. So, but there is a PR pending. I just submitted it today, so it will be gone hopefully eventually. So yeah, but this is also should be considered when using current version of Spire. Great, and that's probably it. I don't know, we even have time for questions. Thank you very much. I was very glad to give the talk.